let's do some examples of integrals for the natural exponential function. Now we're going to be using substitution here because without substitution this is pretty trivial. The first one is e to the negative x to the sixth times negative 6x to the fifth dx. Now, generally speaking, when you deal with exponential functions, what you're going to do is you're going to choose the argument here as your substitution. So that's your u. Now, that doesn't always work that way. Sometimes you have to be a little more clever, but it's always a first good start. So by doing that, we'll say, let u equal negative x to the sixth. So then when we take its derivative, we say du is negative 6x to the fifth dx. Well, looky there. We have negative 6x to the fifth dx already. And so we're going to replace each term. Let's go in. We'll say this now becomes e to the u du. Well, that's fairly simple, right? E to the u du. That gives us e to the u plus an arbitrary constant. Don't forget your arbitrary constant. Don't do it. Don't forget it. But we started in x's. We didn't start in u, so we have to go back to x's. So we end up with e to the negative x to the sixth plus c. Simple, clean. I like it. Now let's do something that's a little more complicated, but has a similar process. We have e to the square root of 7x divided by that square root of 7x dx. So if we're going to do this, let's try this. Let's say, okay, I'm going to let u equal the square root of 7x, which is like saying the square root of 7 times x to the 1/2. Because that might make your life a little easier, maybe. So then what we're going to do is we're going to say du is 1/2 square root of 7 x to the negative 1/2 dx. Okay, that's a lot there. So that's going to be du is 1/2 square root of 7 over square root of x dx. Right, because x to the negative 1/2 is 1 over x to the 1/2, and x to the 1/2 is the square root. So we have this. So let's move all that jumble over. Let's just say that over here we have square root of x over square root of 7 times 2 du equals dx. Just move everything over. Multiply both sides by 2, divide both sides by the square root of 7, multiply both sides by the square root of x. We want to do this because what we're going to try to do is we don't want to replace this with a u. We want to actually try to cancel this. So to do that, we're going to get e to the u square root of 7 times the square root of x. I'm going to split those two up, which is perfectly valid. Remember, square roots, you can split that up like that, times square root of x, 2 square root of x, over square root of 7 du. Okay, so this is the reason why I want to do this is now we see that the square root of x's are going to cancel. Square root of 7 times the square root of 7 is just 7. So we have this 2, we have a 2 on the top and a 7 on bottom. We have a 2, 7, e to the u du, which is really clean. A lot cleaner than you might have thought it was going to turn out. The square root of x is canceled. Square root of 7 times square root of 7 is positive 7, and the 2 comes out. So that gives us 2/7 e to the u plus a constant. But again, we started in x's, we have to finish in x's. So that gives us 2/7 e to the square root of 7x plus c. Now, the way you would want to validate this, this one's fairly straightforward. You could take the derivative and find that easily. This one, remember the way you do that is the derivative of the constant is 0. The derivative of this is 2/7 times e to the whatever, which is square root of 7x, times the derivative of square root of 7x. And then once you get the derivative of square root of 7x, what you find is that it will all simplify to get you that. So it's a little bit of extra work there, but it's just kind of part of the process. There's also a way to do this as a double substitution that actually might make things cleaner, but we haven't covered double substitutions yet, at least not really, so I don't want to overly complicate things. Now let's continue on. We have e to the 1 over x to the 8th times, or divided by x to the 9th dx. So what I'm going to do is I'm going to rewrite all of this with trying to get rid of fractions, and I'm going to write this as x to negative powers. So 1 over x to the 8th is x to the negative 8th. And x to the 9th on bottom is x to the negative 9th. So x to the negative 8th times x to the negative 9th dx. That's how I'm going to rewrite that. The reason why I want to do that is that I notice there's a familiarity with x to the negative 8 and x to the negative 9. So I can say, if I pick u to be x to the negative 8th, then du is negative 8 x to the negative 9 dx. So then what I can do is I can get this as negative 1 over 8 x to the negative 9 du is dx. And I can substitute in. So I'm going to bring it over here. So I have e to the u times x to the negative 9th times negative 1 over 8 x to the negative 9 du. So what that's going to do is the x to the negative 9s are going to cancel, and that negative 1/8 is going to come out front. So negative 1/8 e to the u du. At which point we know how to find this antiderivative. It's simply negative 1/8 e to the u plus c. But again, we didn't start in u's, we started in x's, so we have to go back, which is negative 1/8 e x to the negative 8th plus c. And this is a perfectly fine answer. You feel free to leave it that way. It's actually kind of clean that way, but since we started with it looking like this, generally speaking, conventionally what you're going to see is most systems want you to write it like that. So that's probably going to be the way that if you were putting this into an online system, this is probably how they would write it. However, this is a perfectly acceptable answer. It's equivalent. It's just that we started that way, so we're going to leave it that way, right? Finally, we have this. This one's going to require an extra little trick. Because I have an e to the x here, okay? So there's not really, my u substitution isn't really the argument on e to the x. But so the next thing we want to do is we say, I hate what's in this thing. So I'm going to pick this thing to be my u. I'm going to say u is 2 minus e to the x. Okay, that's good and all. Then du is negative e to the x dx. Actually, this one doesn't require the trick. I was thinking it was like x times square root of 2 minus x dx, and it's not. This is actually nothing like this. This is actually really easy. Okay, so du is negative e to the x dx. Well, then rewriting this, this is 2 minus e to the x, e to the x dx. You can kind of write it like that. So then, if this is true, then that's true, sure. So we can just do direct substitution. We end up with square root of u times negative du, negative square root of u du. Now, we don't want that. We want u to the 1/2, right? Square roots are not fun. So we're going to write that as, I'm going to pull that negative out here, u to the 1/2 du. And then we just add, so we say negative u to the 3/2 divided by 3/2 plus c. But that's pretty ugly, so we bring that up and say negative 2/3 u to the 3/2 plus c. Okay, great. And we started in x's, so we need to finish in x's. So negative 2/3, 2 minus e to the x to the 3/2 plus c. Easy peasy. Nothing too hard there. But ultimately, just getting comfortable with using u substitutions with exponential functions is very important. It's going to be kind of your bread and butter here, and it's going to lead us into more complicated substitutions as time goes on. So make sure you get yourself familiar with this.